In this last video dealing with the functional groups in organic chemistry, I'm going to talk about the esters and amides. These are often referred to as carboxylic acid derivatives because they evolve from a reaction between a carboxylic acid and something else. So we're going to talk about that a little bit. So here we have an ester functional group, and you can see by the ester functional group we have this carbonyl group and we have this single bond O attached to the carbon. Okay, so that's pretty important. We'll look at that in a second. In an amide, we have the carbonyl group, as you can see here again, and attached to the carbon of the carbonyl group is a nitrogen, single bond nitrogen. And again, we'll see where that originates from in just a minute. Just to quickly indicate some potential uses of these compounds. Well, esters, here's an ester molecule. So it's actually, if you count the carbons from the single bond O, we have 1, 2, 3, 4. So that's a butanoate component of the molecule. From the C double bond, we have 1, 2, 3, 4. So that's butanoic. That came from butanoic acid. So what this molecule is actually known as is butanoate, and that gives a particular odor, and that odor happens to be pineapple. So butanoate as a chemical is sometimes used as a food additive for the scent or essence of pineapple. Amides, on the other hand, not quite as simple to explain the uses, other than amides are very often polymerized. So polymerized simply means you take an amide and you add a bunch of amides together to make a long chain macromolecule known as a polymer. And a polymer that contains an amide is nylon. And so we're going to talk about that more when we talk about polymerization. But anyways, just a couple of uses of these molecules. So let's talk about naming. So esters, first of all. So as I mentioned, the esters with their functional group, the C double bond O, originates with a carboxylic acid. This O and the rest of the chain originate with an alcohol. And so it is an ester is formed via a condensation reaction between carboxylic acid and an alcohol. And that really gives us a lot of guidance in trying to name them. So the ester functional group now has this single bond O as part of the chain. Okay, so now that's part of the chain in your molecule, and it's a good dividing point. Actually, the dividing point is this bond that gets formed between the carboxylic acid and the alcohol. That bond is known as an ester bond. And so it gets formed in the condensation process. And so if we look at our example here, we have, this is ethanol, and this is propanoic acid. So there are my two reactants for my reaction. And here's that ester bond that forms between the two. So when we name it, we take the alcohol component, so that is ethanol, with the oxygen, and we treat that simply as a branch, and so that becomes an ethyl branch. So it's ethyl, and we take the carboxylic acid component, so that's this bit, which is propanoic acid, and we take the oic acid off and we add the suffix -ate. So instead of propanoic acid, it becomes propanoate, propanoate. And there is a space here. This is one of the few times you have a space between what otherwise appears or look like a branch in a root name. So ethyl propanoate originates from ethanol, the ethyl component, and propanoic acid, the propanoate. And the functional group is recognized then as this C double bond O within the chain. It's really important you realize this ester functional group must be within the chain. So again, a little bit of practice, and for my mind, what you want to do first is identify the ester bond. So there's the ester bond, which means this came with the alcohol, and that's going to give you your branch component, so that becomes an ethyl. And this originates with the carboxylic acid, and now that's 4 carbons long, so that would be propanoic acid, butanoic acid. So this becomes ethyl butanoate. And so there it is. Ethyl methanoate. Well, now if you're drawing it, you have to realize this came with the alcohol. And so as an alcohol in that ester, we're going to draw that O with 2 carbons. There's the ethyl component that came from ethanol in the condensation reaction. Methanoate is the carboxyl component, so there's my C double bond O, but it's a single carbon, so I just add a hydrogen, and that would be methanoic acid. So there is ethyl methanoate as an ester. So let's have a look at this now. Given methanoic acid and 1 pentanol, draw and name the ester as formed. Well, sometimes it's useful to draw the molecules first because they're going to give you some guidance. So we can quickly scratch out methanoic acid, C double bond O, OH with the hydrogen. So there's my methanoic acid plus 1 pentanol, and so that's going to be a terminal carbon on a 5 carbon chain. And then I'm going to add hydrogens. And there is my 1 pentanol. So the reaction that takes place, this condensation reaction, occurs at these components of the functional group, and the oxygen stays associated with the carbon chains of the alcohol, but the hydrogen is lost, and the OH group on the carboxylic acid is completely lost. This is why it's called a condensation reaction, because you get water. There's your water, and you get your ester, which is going to look like this. Double bond O, and then O, and then 5 carbons. And hydrogens attached. And what would that be called then? Well, there's your alkyl component, so that is pentyl methanoate. Pentyl methanoate is the ester, forms from methanoic acid, 1 pentanol, and the other product of that reaction is water. So esters have a polar functional group. The delta N is about 0.8 for a C double bond, and there's same delta N for the COC component in the functional group. So it will have a bond dipole and is molecular dipole, but this dipole is not as strong as you would see with alcohols. So similar molecular mass ester like methyl methanoate, boiling point's only about 32 compared to 82 for propentuol. So even though they're delta negative components to this molecule, they're a bit weaker, and part of that is sort of access to those polar components. It's just a little hard to slide a molecule in because they're bigger and more bulky stuff in the way. So methyl methanoate, lower boiling point, which is typical of esters, but they are quite soluble in water. They'll dissolve very well, but we'll talk about that later. So on to the amides. So amides, like esters, originate from a condensation reaction, but in this case it's between an amine and a carboxylic acid. And we can see that with a functional group. There's the C double bond O that originates with the carboxylic acid, and there's the bond N that originates with the amine. So we form this single bond between carbon and nitrogen, and that's known as a peptide bond. And we form that bond when we allow a condensation reaction to proceed. And so the functional group, carbonyl group, with the added nitrogen, single bond and nitrogen, and the name for amide is much like that for carboxylic acid. The component that comes or originates with the amine is going to have the N bonded to it, and it may have an H, it may not, it depends. But so this originates with the amine, and that becomes an N branch, and so that's what I have written down here. It becomes an N substitution, and I'll show you how to deal with that in a second, but that's an N branch, so you've not heard of that before. And then the other component of the molecule originates with the carboxylic acid. I have this drawn the opposite way. It's going to bond here with this carbon, and this becomes your amide component. So we just add amide, the suffix, to what would be an alkane name. So if we have a look at this particular molecule, here's our peptide bond. This is your N substitution. There's the nitrogen. Here's my functional group. Let's just make sure we realize the functional group. There's my amide functional group. And so this nitrogen and what's attached becomes an N, well, this what's attached is an N substitution, so that becomes N-ethyl. That came with the amine. And what I have here is a 1-carbon carboxylic acid, methanamide. So we designate that as an N substitution because it's off the nitrogen of the functional group for an amide. Let's have a look at a couple more. So if we were to name this one, let's just first highlight the different elements of it. So here's my C double bond O, there's my peptide bond, and so this came with a carboxylic acid, and so that's going to give us our compound root name. This came with the amine, and so that's going to become an N substitution. So this molecule would be called N-ethyl. 4-carbon carboxylic acid, so that becomes butanamide. So an N branch because we have this ethyl group bonded to the nitrogen of the functional group. N-ethyl and methyl ethanamide. So this is a little different, but we can draw our ethanamide first, which is C double bond O, and what's attached to the ethanamide is simply another carbon. So this component came with our carboxylic acid, which must have been ethanoic acid, bond N. So there's the functional group, the amide functional group. There's my peptide bond that was formed, and so what I have attached is N-ethyl and methyl. So I have two N branches, and that should be fairly straightforward to identify. Remember, nitrogen often forms 3 covalent bonds. It's always going to have that lone pair still there, though. So N-ethyl, there's the ethyl group, and methyl, there's the methyl group. N groups because they're bonded to the nitrogen. Ethanamide, 2-carbon component. How about this last one? So again, there's my functional group. C double bond O came with the carboxylic acid. NCH, that came with an amine, so that would simply be N-methyl methanamide. All right. Amides in polarity. Well, again, polar with 2 components to that functional group that are polar. So that C double bond O is polar, and the NH bond is also polar, 0.8. So amides will be polar molecule, and they can have quite a strong or high boiling point because they have these 2 components that have the capacity to form intermolecular forces, and one of which is hydrogen bonding, and that's from the NH. NH will form hydrogen bonds with neighboring molecules, and as I mentioned in a previous video, hydrogen bonds are strong. They will also form dipole-dipole forces with other molecules because of the polar nature of the C double bond O. So as a result, small molecular mass amides can have very high boiling points because of this capacity for hydrogen bonds on top of dipole-dipole forces. That changes as molecules get bigger, but that's for another conversation. But you can compare it. That's quite a bit higher than similar molecular mass alcohol, which also forms hydrogen bonding. Remember, that force attraction there is going to be hydrogen bonding because of the OH group. So amides, unusually high boiling points, and it's mainly due to the capacity to form hydrogen bonds as well as dipole-dipole forces. So quickly, just to summarize, we've talked about two carboxylic acid derivatives, the esters, and here's an ester functional group, and the amides. And the esters originate from a carboxylic acid, and that's shown here. This component would come from a carboxylic acid. And this component then comes from an alcohol. So a condensation reaction between a carboxylic acid and an alcohol produces an ester, and it also produces water. The amides originate with a carboxylic acid, hence both of them are carboxylic acid derivatives, and it also reacts with the amine. So this carboxylic acid reacts with an amine, and you get an amide. And you also get water. So they're both condensation reactions. So that summarizes the ester derivative, or carboxylic acid derivatives, esters and amides. Both polar functional groups, both have somewhat complicated functional groups. But again, I think if you appreciate where the components in the name come from, you can quite easily name or draw these molecules. And that concludes this video.